Let me thank you for visiting my channel. In this particular video, we are going to discuss the algorithm to find optimum solution in calculus. There are three different variations and all the three will be discussed in this video. It will be about 25 minutes long. Thanks and enjoy the journey with Anil Kumar. I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll take up optimization question, very important question from test point of view. Along with solving the problem, we are also going to understand the algorithm. Algorithms followed for optimization questions in calculus have three variations. All the three will be discussed in this video. In my playlist, you can find hundreds of examples which are based on optimization, which is basically finding the least or finding the maximum value of the variable in question. The question here is a conical cup is constructed from a circular piece of paper of radius 5 cm by cutting out a sector and joining the resulting edges. What is the maximum volume of the cup? Now, how should we begin with this problem? The equations are not given to us. Very little information is given. Following an algorithm really helps. Now, what kind of algorithm can we follow? First thing is we need to really understand a question. So, I'll show you the steps followed in the algorithm so that we will understand what exactly to do with this particular question. Most of the time, when I say algorithm, we'll follow this algorithm most of the time. There could be variations depending on the given problem to us. So that's a very important point to understand. Normally, the step one is identify what is to be optimized, right? So in this particular question, we need to optimize the volume, which is to be maximized. Then draw a diagram to understand the situation. Define and relate variables. There are many variables involved when we are checking the volume, correct? Write a function in one variable. Now, this is kind of very critical. Writing a function in one variable. Then we have to find the critical points, which basically is first derivative is either 0 or it does not exist. Once you find the first derivative, after that, there are three different ways of finding the optimum value, and based on those three different ways, we'll take up at least three different videos for you. One is called absolute optimum value. In absolute optimum value, we are given the interval, a range from this to that, both endpoints included, right? So in this case, we include from A to B, right? In that case, the optimum value can be at A, can be at B, or at C, which is our critical point, right? So normally the critical point will be at C, right? So we are equating this. So at C we have to find. So we just compare these 3 points and get our solution. The other two methods are one, to analyze the first derivative itself. If it changes from increasing to decreasing, that is to say, if the first derivative, this is the first derivative test, right, to decreasing, in that case, we know it is the maximum. However, if it changes from decreasing to increasing, then we have hit a minimum value. Makes sense, right? Now, after finding the critical points, we can also do second derivative analysis. Now, very few students normally will do second derivative. Second derivative actually gives us concavity, correct? So, if the second derivative is greater than 0, let us say, right, at any point C, greater than 0 means it is concave up, and that means we are hitting a minimum. You get the idea. And if it is less than 0, in that case, we know that we have hit the maximum. You get the idea. So, finding second derivative at that critical point also helps. So, I think algorithm is absolutely clear. So, these are all the steps to be followed. You can change the order a bit, right? However, cover all these things while solving a problem related to optimization in calculus. Is that clear to you? At this stage, let me also thank all the viewers and subscribers for watching my videos, appreciating them. We are also looking forward for some of you who, if they can, also support quality education. In that case, please send an email to us and discuss the options for quality education worldwide. Thanks for your support. Let's now begin with the solution. So now let's begin with the solution of our question, which is right here. So let's read the question once again. It's a good practice to read the question and understand it. Okay. A conical cup is constructed from a circular piece of paper, right? So let me just sketch a circular piece of paper from where we are going to construct this conical cup. It is of radius 5 centimeters by cutting out a sector. So you have to cut out a sector to make this. So let's say this is the sector which we are going to cut out. And joining the resulting edges. What is the maximum volume of the cup? Right. So once you cut it out, then you make a cone. That is the cone. Correct? Radius given to us is 5 centimeter. Therefore, this side will be 5 centimeter of the cone slant. Is that clear to you? Now, it says, what is the maximum volume of the cup? So, we need to maximize the volume. Okay, so what is volume for us? Volume will be 1/3 pi r square h. Now, we don't know r and h. We know 5, right? So, let's find what r and h are. So, these are the two things which we need to figure out, r and h. Correct. So we have a formula for volume which needs to be maximized. However, this is in two variables. Correct? Our focus should be in writing this as a function of one variable. Okay, so we can relate r and h with Pythagorean theorem. Correct? So let's relate. R square plus h square equals to 5 square. So r square equals to 5 square minus h square. Perfect. So why did we write r square? We could have written h square, then there would have been square root. In the formula you see, we have r square. So it's better to write in terms of r square. Simpler equation to work with. Very important, right? And clearly, now we could rewrite the volume as 1/3 pi. Instead of r square, we'll write 5 square minus h square. And we already have h here, right? Is that clear to you? Now we have a function in one variable which is the height of the cone. You get the idea. So this is a very critical step which you should come to before beginning to differentiate. Let's open the bracket just to simplify it further. So 1 by 3 pi, 5 square is 25, right? Minus 1 by 3 pi and h also, right? Just multiply with h and 1 by 3 pi h cube. Is that clear to you? So we have our expression which is now we know what the volume is. So let me rewrite this expression. The function volume with respect to height as a function of height is, we can rewrite this as 25 pi by 3 h minus 1/3 pi h cube. So that is a very critical step, writing a function to work with, and that too in one variable. So do you see this now? Now this is in one variable. Now what you should do? You should differentiate this, right? So let's differentiate. So volume differentiating with respect to height, the variable which we related with, is 25 pi by 3, correct? Minus 1/3 pi 3h square. Let's simplify. 25 pi by 3 minus 3 and 3 cancel, pi h square. So that becomes the volume derivative. Critical number means I have to equate this to 0 to find the critical number, right? So once you equate it to 0, you can easily find the critical number, right? So we are now finding critical number. Perfect. That means pi h square is equal to 25 pi by 3. And that gives you the value of h, right? Pi and pi cancel, correct? Just cancel, right? And we have square root of 25 by 3. So plus and minus normally, but we know it is always positive, correct? And we have 5 over square root 3. So we did the square root of 25 is 5 and square root of 3. So we get 5 by square root 3 as a critical number. So for us, that is the critical number. So now, as I said, once we find the critical number, so our point C is basically equal to 5 by square root 3. Make sense? Now we need to analyze this particular derivative, whether this point is indeed a maximum or not. Is that clear to you? Correct? So as I said, there are three ways of doing it. One, we could also use the extreme values. So let's write the expressions which we have. One to analyze is the volume itself. The second one is the derivative, correct? These are the two things which we should be considering, right? So, okay. So all the three expressions, we'll take it on the next page and then redo it. Okay, great. So let me write down all the three expressions. So we have volume in H as equal to, so as we did is 1/3, let me redo, 1/3 pi r square. R square was 5 square minus h square. H, correct? So this was our expression. So I'm just redoing all the things. So volume expression which we got when we open this up is 25 pi h by 3, correct? Minus pi h cube by 3, correct? And the derivative which we got was 25 pi by 3 minus 3 and 3 cancel, pi h square. And the critical point was at h equals to square root of 25, which is 5, over square root of 3. So that is what we have come to. Now, as you can see from that particular cone, let's redraw it here. So as far as the height is concerned, the value of height can be maximum, it can be 5, right? And minimum, it can be 0. So those are the two extreme values. Correct? And our critical number is 5 square root 3. So what we can do is find the volume when height is 0. So in that case, clearly we have volume 0. And also we can find the height when height is 5. We can find the volume when height is 5. And clearly that is also 0. That means that the volume at critical point is a maximum because we know it is not 0. So from the extreme value, it is very easy to verify that we have hit the maximum at 5 by square root 3. You get the idea, right? So that is one way of doing it. So this was our option 1. Correct? Option 2 was to analyze this particular derivative. So we'll do option 2 also here. So we are analyzing the derivative. We have a critical number which is at 5 by square root 3. Correct? Now we can take 2 points, one on the left side and one on the right side. Correct? So these are called the test points. So 5 by square root 3 less value will be what? So let's see the decimal equivalent of 5 by square root 3. It is around 2.8. So let's take this point on the left side as, let's say 1. And on the right side, let's say 3. Or you can say 4. Any point you can choose. Now once you have these points, in that case, plug in the point in the derivative. Correct? So derivative is 25 pi by 3 minus pi h square. Now when I plug in 1 here, in that case 25 by 3 is greater than 1, so we get a negative value. Correct? So if I plug in 1 here, then we have 25 pi over 3, which is greater than pi 1, right? Just pi, correct? So this we get a positive value, correct? But I substitute 4, we are taking out a very high number, right? And therefore this value will be negative. And what we see is that the rate of change changes from increasing to decreasing. And therefore this point is a maximum. Makes sense? So this was using the second method. We can also use the third method, and that is we can find the second derivative and check whether it is positive or negative at a given point. Now the second derivative will be 25 pi over 3 is 0 derivative, right? It's a constant. And then we have minus 2 pi h. Now for h equals to 5 by square root 3, we see that the second derivative is less than 0. And clearly, that means concavity, it is concave down. And therefore, we do have a maximum. Makes sense? Concave down. So we have a maximum volume at height equals to 5 by square root 3. Is that part also clear? So I have shown you with one example all the 3 algorithms for optimization, correct? Now the question is, what is the volume, right? So you can use the calculator and find the exact value of volume. We have the expression here, right? Which is volume is 1/3 pi 25 minus h squared times h, correct? But we can calculate the value on the next page. So we'll rewrite the expression, which is volume is 1/3 pi r square. R square was 25 minus h square times h. And the value of h we are looking for is 5 by square root 3. Makes sense. So I hope with this, your concept of optimization while working in calculus are absolutely clear. Well, in case you want to learn directly from me, feel free to send an email on globalmathinstitute at gmail.com. Our students are right there on the top. So, well, let's use the calculator and find the volume for the value of h as 5 by square root 3, right? So, basically, plug it in, right? 25 minus square of 5 by square root 3 whole square times 5 by square root 3, correct? So let's calculate this and write down the expression. So, so we can write down this as 1 divided by 3 times, I'm writing 3.14 for pi, right? Times 5 divided by square root 3. And then within brackets, we'll multiply by 25 minus 5 square, which is 25 divided by 3, correct? And this is equal to 50.3577. So we can round this to approximately 50, right? Centimeter cube. Does that make sense to you, right? You can do the calculation once again, right? So that is how we get the expression, and then we find the maximum volume using three different ways for optimization, which are discussed in our algorithm, correct? So you see in this particular example, we discussed all the three methods, right? Now we just need to write down the solution very clearly, and the solution is that maximum volume is 50 centimeter cube of the cone, right? So that is how I think you should be doing. Well, in case you want to support us, feel free to send an email on the given address. We can discuss plans to support quality education. Thanks for your time and all the best.